Okay, good afternoon. Welcome to the lecture 3. We will conclude our discussion on examples of optimization formulations. We have already seen several discrete versions, several continuous versions. We'll see some more discrete versions and then move on to basics of continuous optimization and convexity. A lot of it I'm going to give it as reading for you for homework. So recap from the last class, we talked about map inference and probabilistic models. I gave you the example of part of speech tagging, but let me very quickly also present the case in the use case of icing models. So the idea behind icing models is that you're often trying to identify a low energy configuration. Let's say you have a bunch of electrons and their spins, right? And you want to find a configuration such that the energy is minimized. So should be whether this should be positive or negative, whether this should be positive or negative. Well, it depends on the energy between these adjacent nodes, and also depends on the energy associated with the particular spin of a particular node. So we're trying to find an X such that this energy configuration is minimized. Now you can give a lot of probabilistic semantics to it, uh, where you're looking at attractive potentials. You could also have semantics associated with repulsive potentials. Okay, so that's where a DPP is come, where you're looking at not cooperative, but right, you're looking at somewhat repulsive. If one is positive, the other should be negative. Whereas the Ising model is more about attractive potentials. I'm sorry, the Ising model is which looks at positive and negative, and DPPs might look at diversity. Okay, so there are different probabilistic models and semantics associated, and accordingly, the the low energy configuration could change. Um, but let's look at some other examples. I'll run through some of these in the following slides. As I said, you could also have natural language processing, where you're looking at the part of speech tag sequences associated with a bunch of words. And there you're trying to detect, say, phrases, you're trying to detect n-grams, semantic structures. And the overall idea there is that you are trying to maximize, again, find an sequence, say an argmax of the parse structure. Uh, just call it parse of the probability of the parse given word sequence. That's the most generic formulation. Okay, so I gave you an example last time. If you have a sequence of words, this is say 13th of January 2022. So that could be the word sequence. And what you're trying to find as part of the parse could be the phrasal structure associated, the fact that 13 January 2022 is a date structure, but it's more specifically a noun phrase. This is um, a pronoun and so on. Could also have a parse tree, where you're looking at a tree structure association. In computer vision, I'll give examples of image segmentation and image correspondence. That those are examples coming up. Okay, with this, let's move on. Again, as always, please feel free to ask questions. So the first is of image segmentation, and then there's a related problem of image correspondence. But let's begin with the second problem here. This minimum cut problem, which I mentioned here. So what are we trying to do in image segmentation? So you have an aeroplane flying in the sky, and you want to identify the boundary of the aeroplane. How would you like to do that? Well, imagine that you had lots of nodes here. Okay, so this is a node U, this is a node V. Now the U and V you believe should belong to one region of the image, And the energy associated with having both of them as a background is say 0. On the other hand, the aeroplane itself would have or pixels in the aeroplane itself would have again 0 energy association. What you would like is as you go from the aeroplane, a pixel in the aeroplane to a pixel outside, let's say this is P and this is Q, the energy associated with PQ, you would like that to be high, which means that you would not like them to belong to the same region. CPQ is let's say very high, 100 or whatever. I mean, I've not really normalized these. So what you would be interested in as part of this optimization problem is something like min. You want to again minimize the energy, like I've said in the previous slides. Now you want to segment this into two parts, which is what you're trying to determine. See the part S, which corresponds to the aeroplane, and of course the part which doesn't belong to the aeroplane. So let's um, call this S, and then there is S complement. I have a min over S of all the pixels U that belong to S, all the pixels V that belong to S complement of the cost associated with U and V of the edge connecting U to V, right? So obviously, U and V, U and V range over all the possible edges. Okay, so this is sum over all the edges. So if you want, you can add that here, U, V, the set of edges. Okay, the whole thing is for the index for the summation. Okay, so this is a minimum cut problem. The segmentation problem. Now it turns out that if you have some interesting properties associated with the C, often they're referred to as, again, submodularity constraints. You can actually solve this problem, the problem of finding this S in polynomial time. So minimum cut problem. On the other hand, you also have bipartite matching, which you can view as a maximum flow problem. What's the bipartite matching problem here? Okay, you have these two images and you're trying to do a correspondence. You're trying to determine which pixel in the image on the left corresponds to which pixel on the image on the right. So the pixel set of pixels of the image on the left, you can call them U, and these are V, and that's what we have shown in the image on the left here. Now, how do you frame this problem? So all of you have, some of you have taken algorithms course. You have heard of the Ford-Fulkerson algorithm, and you know that there is an entire area of formula of problems called maximum flow. So you could do the following. You can formulate this matching problem where you're trying to find the correspondence of pixels in U with V as a max flow problem. Any suggestions how you do that? I've given you an example of the cut. Could you suggest how you would do, how do you formulate the bipartite matching as a flow problem, max flow problem? Anyone? Yes. As mentioned earlier, this is meant to be interactive, and it's okay to make mistakes.
So can you please repeat the question?
So you understood how the segmentation problem, right? Image segmentation problem has been formulated as a cut problem, right? Formulated the image segmentation problem as a minimum cut problem. So I would like to you to formulate the correspondence problem as a maximum flow problem. image correspondence problem at the top.
Sir, in this case, what would be our source and what would be the sink? Because a max flow problem has a source and a sink.
Any suggestions?
We can add them on our own.
We can add hypothetical source and sink. Where would you add them?
The source can connect to all the vertices in U, and all the vertices in V can end up in the sink.
Okay, great. So here you have S and your T, right? And your suggestion was we can connect. These are hypothetical edges connecting S to every vertex in U. Likewise, I can connect every vertex in V to my hypothetical T. Next, what do I do?
So make it a directed graph.
Okay, directed. Treat this to be a directed graph. What can I put some capacity on these edges?
Yes.
What would be the capacity?
Capacity of 1 on each edge.
Capacity equals 1 on each edge here. Okay, and what else would I do? The rest is simple. If I just try and maximize the flow, I have a matching. What would the how would I uncover the matching based on the flow? The edges which have saturated their capacities, right? Which are basically 1. The rest should have 0. Correct? So I mean, the way you would formally write down this problem is max. Again, now you need to identify the variable on which you want to maximize, right? What do you want to maximize? Basically, you want to maximize the flow from S to U, right? But this is for all the edges in the SU edges in E. Okay, so this I'll just shade this. This is what you want to maximize, such that, but there'll be a constraint. What's the constraint? For any node P, just use P as hypothetical node, right? What should be the incoming flow to that node versus outgoing flow? What should be the sum of QR in the edge set E of the flow from Q to R? I'm sorry, this is Q to P. Q to P. What would the expression between this and say P to R in the edge set E of FPR? The expression
Will be equal.
right? That's it. So that's what. Okay, so what you're basically saying is that, okay, let me just give it a different. Okay, so we are saying that these basically correspond to any set of Q that get connected to a vertex P as incoming edges, and then P outgoing to say R. Okay, this P could be any node in V, in the set U. It could be any node in the set V. Okay. Any questions? Oh yeah, we'll further also have these constraints that F E and the yeah, any FP QP should be greater than equal to 0 and less than equal to 1. Okay, so you probably know the augmentation algorithm, right? You'll keep augmenting a path. If you don't know, then that's taught in a basic course on algorithms. But for us, the interesting thing is that we can formulate all of these as optimization problems, and then we'll look at some interesting characteristics of these. Okay, any questions? Can we move on? Okay, so I mean, just to understand this graph as well, what you're trying to do here is understand the foreground S, the aeroplane, from the background T, which is in black here, right? And then you're doing that using this S, this cost associated with edges. You would like edges within the foreground or within the background to have low cost, and edges going across them to have higher costs. The next application is feature selection. So if you have a machine learning model, you want to identify a subset of the features based on some measures such as mutual information. So what is mutual information? The mutual information by default is always associated with entropy. Okay, but let's define this. If you have H entropy, the mutual information between random variables x1 and x2 is the mutual information, the entropy of x1 plus the entropy of x2 minus the entropy of x1 and x2, the joint entropy of x1 and x2. So this is like saying how correlated are the two random variables, right? So can I make use of this? Identify good features. So the x1, x2 are random variables, and I'm giving you mutual information. Can you suggest how I could make use of this to determine the right set of features, which is often also called the process of feature selection? So as a hint, I must tell you that you should not just consider x1, x2, but also you should consider the class variables. Okay, let's consider also the class variables y. I'll just type it out. It's just a class variable y. So you could also compute the mutual information between x and y. Likewise, right? The same expression between any random variable x and the random variable y, which denotes the class. So with this hint, would you like to suggest what would be the optimization problem? When that mutual information denotes the information, the kind of a notion of correlation. Entropy, I'm assuming all of you know, right? Entropy of a discrete random variable x is negative of summation over all values that x can take of x log p of x, and it basically captures the average amount of information or bits that I need to encode about the variable given the distribution, the uncertainty. So if the x is extremely high entropy, right, and you'd know that it's very uncertain, right? For example, uniform random variable in the case of uniformly distributed random variable, in the case of a discrete random variable, has very high entropy. So what would you like to do? You'd with respect to mutual information, Any suggestions? Anyone? What would be the goal? I'll probably help you through one more slide. Okay, so what is the goal? A goal is to select a subset of features. So that set of a subset of features are as good as the original set. So what is my yardstick of goodness of feature? It should help me predict the class, right? So based on this, can I consider maximizing the mutual information between the set of features and the label Y? So I want a set of features. Okay. I want a set of features A, subset of features A from this entire collection x1 to xn such that the mutual information between xa and y is maximized. Okay, so now it turns out that this is set function. Now this inherently is in terms of entropy. Okay, H is denoting entropy. Entropy. What we can do is also replace that H entropy with some other function. In fact, entropy turns out to be a submodular function. Okay, and as we've shown, and it can be replaced by several other submodular functions. I've not defined submodular functions precisely, but I'm just going to give you an idea right now to get different notions of mutual information, different measures of mutual information. Okay, but the key idea here is that you can now templatize and create lots of other functions. For example, what is a submodular function? It's basically a function which has diminishing returns. Okay, a submodular function would, for a discrete optimization problem, should behave like this. So if I pick one element x1 and then I try and add another element x2, then the gain I get is so much. But then when I add a third element x3, okay, the returns are diminishing. Add another element x4, further diminishing. It may not decrease. It may be still monotonically increasing. If you were to, you can interpolate across these, right? But this is a discrete function, and therefore it might be a little dangerous to do the interpolation. But what we see is a discrete function diminishing returns. That's what a submodular function is, and it behaves very much like convex functions. Okay, concave functions. So these functions, okay, behave like concave functions. So what are concave functions? Well, they are cup shaped. You have done a basic calculus course, you would certainly come across convex and concave functions, but the concave functions are also cup shaped. They also exhibit diminishing returns. Okay, so in that sense, they behave like the discrete functions, which are submodular functions. They behave very much like concave functions. Okay, and because of that, maximizing some modular functions like concave functions, right? If you want to maximize a concave function, you would look at this point at the peak. So from maximization perspective, their behavior is, I mean, they do inherit some good properties from concave functions. It's another thing that some modular functions also behave like convex functions when it comes to minimization, but we'll talk about that later. Okay. But what is relevant here is that understanding concavity, convexity helps also appreciate discrete optimization problems through the lens of these special class of functions called submodular functions. And it turns out that there are some very efficient greedy algorithms. Now here we are not only looking at submodular maximization, we are also trying to put a constraint. So notice the constraint. The constrained submodular maximization problem. Okay. Okay. Any questions? Why is this interesting? Well, you may say, let me explore the space of all possible subsets of random variables. What is that space of subset of random variable? How many xa's are possible? Anyone?
2 per n.
Yeah. So the this is a challenge, and that's why we are talking about efficient algorithms. The space is the space of A's to explore, right? Is large. So if we have an efficient way of exploring the space for the class of functions which have some properties like diminishing returns, certainly we can get effective solutions to machine learning problems, especially in the case that the variables themselves, these random variables themselves, have to be fed into a machine learning model. Right? So we'll see in the second part of this course this relation of mutual information to larger class of some modularity. In fact, if you can look at our IIII, sorry, this is a 2022 paper. I put the link here. Prism, where we expand the notion of mutual information based on entropy to several other submodular functions. Look at another application. Please do ask me questions at any point of time. So, yeah, this Prism generalizes a mutual information beyond entropy. Okay, the next class of problems is training data subset selection. So you're given a large training data set and you're given a budget. You don't want to make use of the entire training data set. Okay, so the budget K is on the size. So I want from this D, I want a subset D prime such that the size of D prime is K. But not only that, I want the D prime to be such that it is as good as the D. Now, how do you measure the goodness of the D prime, which is a subset of D? Okay, so let's look at that in the next slide. So I want a subset of data points in this case, which are such that the model trained on the subset is as good as an entire data set. Okay, so I'll just let me add. It's not just D subset of, so D prime subset of D, but we want to optimize. We want to make sure that the model trained using the D prime, I mean, I'm calling it A. So So if you want, you can think of this this D prime is indexed by A. Okay, model trained on the D prime, which is be given by the A, on say on validation set. So I want to measure the performance of this model on validation set or some held out set and make sure that that is compatible or is approximately the same, if not exactly, as the performance of the model trained on the entire data set and validate and evaluated on the validation set. Okay, so this is what we're talking about here. So you're saying the model trained on the subset of data is as good as the entire data set. Okay. It's a little challenging. I mean, you see, note that we have to actually train the model and in retrospect find out, can we do it in a more principled manner? We'll again note the challenge, right? The challenge is that there are this A itself, there are 2 raised to n possibilities. For A, how do I search such a large search space? And so this makes more sense when the labels are say missing on some of the data points, right? So you may not even have the Y's available on all the data points. Some of them may be missing. That's what we mean here. That that is even more interesting, where you want to now identify a subset and also label that subset. In such a setting, we might even want to identify the subset which is worth labeling, right? Okay, so we are making the problem even more complex. So overall, this could be an optimization problem, right? If D is say a distance, some measure of distance between 2 data sets, it could be through the distributions on the data sets, it could be through gradients. All of these are possibilities, though there are specific instances. So overall optimization problem is, I want to, I'm sorry, this distance would be minimized. Here I can put a negative. So I'm trying to minimize the distance, that is maximize the similarity. So this is an optimization problem, which is again combinatorial. And again, this is benefiting a lot from some modularity. We have several papers last year which leverage this data subset selection. And again, some of students here on the group are actually also working on extensions of the paradigm. Specifically, I'd like to point out one very, very powerful paradigm that we've developed in grad match specifically, where we did gradient matching. Okay, we said, what if you try and identify the XA such that the gradient on the loss, sorry, the gradient of the loss function on the subset identified by A is as close as possible to the gradient of the loss function on the entire set V. Okay, with the distance measured say through an L2 norm. So this could be another optimization possibility, and that's what we showed some very interesting properties of such a formulation in grad match. Okay. We'll certainly do this in the second part of the course. Yeah, but to make sense of, even such formulation, you need to understand gradients. We'll need to understand convexity, because convexity comes to rescue, especially when we want to show convergence. Now, you may not deal with convergence of loss functions with respect to an entire deep neural network. Grad match, what we do, for example, is look at the last layer gradients. last layer of a neural network. The gradients of the last layer of a neural network. Now, if you start measuring them, the last layer of a neural network actually behaves like a logistic function. With the logistic loss, we are actually dealing with a convex optimization problem. So the next part of the course, we'll really understand convexity, because convexity, any kind of convergence you want to prove, even the discrete optimization problems for machine learning, either you're interested in convex regions of a function or convexity with respect to certain parts of the network architecture, even when you're dealing with complex network architectures yielding themselves to non-convex loss functions. Okay, so just to sum it up, showing convergence of say grad match uh, certainly requires requires convexity calculus. um, Especially right when and many of these are um, with respect to the last layer of neural networks. Okay, so this is just to give you uh, a strong motivation for what's going to come next, which is a very quick brush up of convexity and a calculus of convex functions, calculus of gradients, calculus of subgradients. All of these are relevant. Okay. Any suggestions, any thoughts, any questions at this point?
Excuse me, sir.
Yes, please.
Sir, what if we try to minimize the variance in the A and the whole corpus?
Minimize the variance.
So if we, I mean, if we able to do that, might be we can, and we can actually predict that the probability distribution from which they come from, maybe.
So you're saying this instead of this D, you look at the variance?
Yes, I mean, minimize the XA transpose XA minus XV transpose XV.
Very good point. So that's another loss function. Very good point. See, another loss function is the diversity. I mean, I won't say it's a loss function negative of the diversity. So negative or decreasing function of the diversity could be another function you want to minimize, or you may be interested in maximizing the diversity directly, right? So diversity within XA. That's what you're saying?
Uh, kind of that. Yes, sir.
Yeah. In fact, this is we consider in several works.
So
Yeah.
that diversity in XS should be equal to diversity in XV, so that we can actually able to equate those distributions.
Very good point. So diversity within XA possibly with respect to XV, right? That's what you're saying. Relative to X.
Yes, kind of.
Exactly. This is exactly what we do in our submodular mutual information functions I mentioned in the previous page, where you generalize mutual information beyond entropy. We do that. But even in this setting, you can directly try and look at diversity of the subset, data subset. Could possibly do it with respect to XV. So all this is covered in the papers that I'm referring to. Yes, it's a very good suggestion, and I think there's a lot that can be done. Encourage you to read our papers and also take up some of these follow-ups as projects. Good point.
So, sir, like in the previous problem, so we can maximize the mutual information in order to
Exactly.
Look
Exactly.
at higher diversity.
Right. So you want high mutual information with respect to XV, but you want XA itself to be diverse. So sometimes you need combinations. There's one function may not fit your bill. We need a combination of those to serve your purpose. But very relevant points. Thanks. Anything else? Can we proceed? A fourth application is Chemidoid clustering. Now this is probably, I would say, the easiest of the lot. So let's say you have two sets of points, two clusters, so to speak. Okay, and you could now try a k-means clustering, right? The k-means problem is a little unfortunate because it might land up giving you the means in no man's land. So this might be a mean and this might be a mean just because there's some outlier points, or maybe it turns out to be here. So the k-means, the means might be no man's land. Okay. When I say no man's land, might not coincide any data point. Okay. Some of them might, but most likely they won't. Right? You're dealing with a given that you're dealing with a continuous search space. On the other hand, what K-Medoid problem says is that no, I want the cluster centers to correspond to actual points. So that's what we refer to them as medoids. Okay. In IEOR, you often talk about facility location. So you have these blue points which correspond to cities or resource areas, and you want to identify facilities that cater to those cities. Now the facilities, you would not like them to be in a completely no man's land, right? You would like them to coincide with existing cities which have infrastructure. So very close, so closely related to the what we call facility location problem. Is almost the same modulo some simple transformation. Okay, so given a set of data points, you're given a similarity function and a budget k. So there's a similarity Sij between any pair of points I and j. So these pair of points will have a similarity Sij. And what you want to do is identify a bunch of data points which can act as the k-medoids. Okay. So we want to identify these medoids. Let me use, yeah. Okay, and I've already pointed out the difference that the means are a part of the original set of points in k-medoid. Now, what's the optimization problem? Do you want to take a shot at it? How would you formulate the optimization problem? We're given a similarity function. What would you like within a cluster? The similarity.
Maximize the similarity.
Within a cluster, right? Within, good. So each point should be assigned to the cluster, rather to the medoid to which it's most similar. Okay. But then the goal is to find the A's. Okay. So this is how you could pose the optimization problem. What is this doing? Is saying that a point in I, every point I is assigned to the point J or the medoid J, which is most similar. Okay, that's what this expression in yellow is alluding to. And then what you want is to find the such bunch of medoids. Now, as you can see, this is again combinatorial optimization problem. Very large search space. Well, how big is the search space here? Let's look at this, right? How large is this search space?
Sir, NCK?
N square.
N square. So note that any kind of partitioning you do of the n, you're looking at two clusters, is it? So any partitioning you do of
Yes.
the n, you'll have lots of possible medoids to be also identified. Right? So let's say this is a partition. Now within each partition, you could have as many medoids as a number of points in that cluster. So that. So can I assume that given a cluster, I can find the medoid uniquely? So these are points for you to think. So instead of trying to identify the cluster, what I'm trying to do is just identify the set of points. If I get the set of points, then obviously I'll get the clustering automatically. So based on this, how many is again 2 raised to n. Right. So if you look at it from the point of view of identifying the subset A, it's actually the power set. Okay. Now the similarity itself could come from multiple sources. It could come from some metric spaces. I mean, you could have a metric, right? For example, where the triangle inequality is satisfied. Could use distance metrics and the negative or the reciprocal, but you could also use kernels. So if you've done a course on machine learning, you'll come across positive semi-definite kernels. So the similarity itself, the SIJs themselves can be chosen very richly. One interesting choice of similarity which we bring out in our submodel library um, is based on gradients. Okay, so you may, if let's say I'm using Chemidoid clustering as part of data subset selection, so you could look at the gradients of the loss function between at two different points, right, to look at the similarity. Okay, so I won't get into the details here, but since I've given a link to our submodel library, we allow for all of that as well. Okay, so do do have a look at our library. Okay. Any other suggestions? Any other thoughts? So again, this comes back to convex concave maximization. If you're trying to say maximize a function of this sort, if you have diminishing returns, and in fact there are diminishing returns. So it turns out that this function has diminishing returns. The function actually looks concave. So this function is connected to some modularity again, and it has this diminishing returns property. Connected to the concept of some modularity, and again, some of the several other papers we have worked with make use of such optimization formulations. This in particular is called the facility location formulation. Okay, big picture, we have given several examples of continuous optimization problems. Today I gave you several examples of discrete optimization problems. But I must tell you that continuous optimization problems are more fundamental when it comes to machine learning. Even if you want to solve the discrete optimization problems, they would have a continuous optimization wrapper. So most problems that we deal with in machine learning are mixed. Right? I give you examples. So most ML problems are actually mixed in this bucket. and the core is actually continuous. Now continuous itself has lots of uh, um, subtypes. This is convex optimization, which within which you have linear and quadratic. But convexity becomes very interesting also because it gives us a way of talking of convergence of algorithms on optimization problems. It gives us multiple things. It also gives us way of handling submodular optimization problems. So convexity is critical. Even continuous optimization problems have regions, convex regions. And these convex regions become of paramount importance when it comes to optimization. So convexity is very critical, super critical. No matter how much we have moved away from non-convex, from convex to non-convex, even for addressing non-convex problems, convexity is very important. But I will not be treating convexity in too much detail. You can refer to, I'll be referring you to some of my previous years lectures if required, as and when required. But I'll give you all the intuitions required for this course. We'll see examples of convex problems such as support vector machines where hinge loss, logistic loss, and logistic regression, least squares we all seen. Submodel optimization, we saw some examples: facility location, set cover, graph cut, and entropy mutual information. Okay, so what we'll now move on to is notations and basics for continuous optimization. I'm going to make it a very quick recap, of vectors, matrices, gradients, Hessians, etc. This is going to be important, and I would insist everyone does this. I'm going to leave some homework problems. You can always look up the internet to get the answers, but please solve them yourselves. Okay, so I'm going to insist. They must be solved yourselves. Okay, and we'll see these for several specific loss functions from machine learning. And the first assignment will also deal with gradients in Python, how to compute gradients in Python, etc. So the road ahead, we'll now build a lot on optimization. We have already seen how statistics plays a key role, and we'll again make a lot of use of matrix algebra as we wade through optimization. Okay, so we've seen optimization is everywhere in machine learning, and now you'll need to develop the expertise to look into the algorithms used to solve and develop new algorithms yourself. This is very key. You will come up with new optimization problems. Just because there's deep learning doesn't mean things have been solved, because data doesn't come cheaply. Annotated data doesn't come cheaply, and all the work we have been doing is about efficient optimization. Many of the IBM research projects I've worked on in the past when I was at IBM in India Research Labs, and subsequently we have always formed new optimization problems. Okay. So next part we'll deal with continuous optimization problems, convexity, gradient descent, as I said, and that will lead us to several interesting algorithms: accelerated gradient descent, Newton and quasi-Newton, and so on. But very importantly, we'll see how a lot of stochastic gradient descent optimization problems can also be analyzed using the tools we are going to develop. And then we'll move on to discrete optimization. We look at linear cost, but more importantly, we'll focus on submodular minimization and maximization. More of maximization than minimization. I have notes on optimal transport. Let's see if we get time. But this is going to be a critical part, the submodularity. I just want to remind you that we'll have assignment. So first assignment we are finalizing. We'll release it soon. There'll be 20%, as I said. Some could be theoretical, some could be practical. Each assignment will have a mixture of the two. And please be, on the lookout for interesting projects. Time and again, as I talk about optimization problems in machine learning, I've been giving hints. Yeah, we could also have a hands-on on decile.org at some point of time, but please go and explore yourself. There's a lot of tutorials we've already put out there. Okay, and please be on the lookout for reading and paper presentation. That's the reason we spent some significant amount of time initially on ML problems and the optimization formulations therein. And we saw some of these like logistic regression, least squares, etc. But you can look for more. You could look for hybrid of supervised and unsupervised, for example. That would be so interesting. Unsupervised will always bring a lot of non-convexity. It can also bring in a lot of discrete flavor. So for projects, do explore problems at the intersection of several of these horizontals, if I may call them so. Okay. So if you have any doubts also on basics of convex continuous optimization, please do let me know as we proceed. But I'm going to go over that a little bit of fast at higher speeds. This is like basics of continuous optimization. What I meant is, if you're looking at one-dimensional optimization. So one-dimensional optimization is basically from calculus. The gradient, the derivative vanishes at the point of minimum. Would you like to recap some of these? So what all do you have? What all do you know from basics of continuous optimization? Let's just list them down. I said, for example, derivative vanishes at the point of minimum and maximum differentiable function. You all know this? So if you have a function increasing and decreasing, the derivative is supposed to vanish at these points. Yes, somebody was trying to say something.
Yeah, sir. The first and second derivative tests, you mean?
Yes. What are the second derivative test? What would that be? At point of minimum, what happens to f double dash? It is, you would expect this to be
greater than 0.
Yeah. So now you're saying we are doing this very loosely, right? What is the necessary condition? What's the sufficient condition? Right? If it's doubly differentiable, the necessary condition is that it should be greater than or equal to 0. And sufficient might be that f double dash is strictly greater than 0. Okay, so these nuances are very important. Anything else anyone else would like to point out? So we want to be able to extend all of these to multiple variables, right? Not a function which is an argument of a single variable, but multiple variable. And we want to be able to talk about the region in which we are able to optimize them. So we'll talk about not only these regions, which are like convex regions. These are convex regions and the convex functions, but we also talk about this range in which we are talking about convexity. And that's a notion of a convex set. And we look at properties and examples of convex functions, relate them back to, again, machine learning at every point of time. There's an entire calculus, like we talk about the calculus, basic calculus you have studied, but there's an entire calculus of subgradients. Okay, we'll look at that calculus quickly. I'll not do all the proofs in class, but some of it will be given for understanding. Glimpses will be provided. We'll be, of course, having detailed recordings from last year if required. So what follows is material for brushing up by the student. And I'm going to basically run through this. And the next class on Monday, I would assume you would have brushed up. Okay. So vectors and matrices. We'll typically use n as a number of training instances and m as a number of features. So if xi is an m-dimensional vector of features, the jth element of xi would be denoted by xij. And what we will use is y for the labels most of the times. We can have an inner product between two vectors w and x. The L1 norm will be denoted by w1 and the squared L2 norm, for example, by norm 2 and so on. Okay, these expansions are obvious. Please ask me questions if you have, otherwise we're just going to rush through this. Now you can also have matrix vector products. All of you are familiar, and the way matrix products with vectors are obtained is by taking one row at a time from the matrix and then multiplying them with the entire vector column. Okay, that gives you just one element here, a11 x1. Right, so these are examples. Again, all this as you're supposed to know. You could also have matrix products, and the way to view matrix products as a stacked matrix vector product, right? By viewing, let's say, B, when you're trying to multiply a post multiply A with B, you view B as a set of P vectors, each of dimension n cross 1, which is stacked up, right? So that's what we have shown here. Okay, with this you can actually view matrix products more easily. You can think of now as AB as AB1, right? AB2, AB P, where these B1, B2, BP are basically the columns of B. So, okay, and this is an illustration of how you would actually do it. Go about the multiplication. Okay, so here's an example of BC. Now as a homework, you can also look at basic rules of derivation, finding derivatives. So for constant, the derivative is 0. You can multiply by a constant and then that constant just comes out. For y equals a x raised to a, the derivative is a times x raised to a minus 1. All these will become very handy when you start looking at derivatives of composite loss functions. Okay, and especially look at the chain rule where composition plays a critical role. If y is f of g of x, then dy by dx is df gx with respect to gx and then dgx with respect to x. And then this is a homework problem for you. What happens if you have fx by gx? So obviously you can think of division as multiplication by the inverse of gx. So yeah, again, if you're familiar, great. I don't want to spend further time. Okay, and here's the examples of for the examples of derivatives. Y if it's log x, then dy by dx is 1 upon x. Now one important point, I will only spend time where I think you wouldn't have probably addressed it in your basic calculus course, which is say the max of x and 0. Y is max of x and 0. So what is dy by dx? Well, we know that if x is greater than or equal to 0, it's 1 and 0 otherwise, right? But I'm sorry, this should have been a strict inequality. Okay, x greater than 0 only. X equal to 0 is a point of non-differentiability. Now what do you do at x equal to 0? The function, is it continuous? Is this function y equals max of x comma 0 continuous? Anyone?
Yes, sir. Yes.
It is continuous. So there a way we can leverage the continuity to still find some equivalent of derivative? And we're looking at derivative analog of derivative at 0. At other points we don't have a problem. So any suggestions? So if you look at the form of the function, what does it look like? What's the form of the function?
It looks like a hinge.
Hinge, yeah, yeah. So now what you could do is at this point, this hinge, you could define the normal, and I will see that motivation later on, but you could define this region, the normal to both, the cone between the two normals, right, to the green regions. This can help you determine something called subgradient. Okay, so you have convex function. I mean, this is convex, by the way. Okay, this I mean, this is cup shaped. We'll define convexity more formally later on, but this is convex. And there are some functions, some points where there is non-differentiability. Okay, so this region in blue, what kind of is reminiscent of something called subgradient. Okay, so let me. So the answer is yes.
Sir, what would be the angle of the cone?
Yeah, let's not get into the angle aspect here. Yeah, I mean you can compute it, right, and geometrically. But the goal here is that there's a non-trivial space. It's not just one point or one value. At all other points, gradient is one value, right? But here you're saying, well, there's a cone and there are multiple possible values. That's what I wanted to say. In fact, there are uncountably infinite number of values. This is when cases for convex functions. This has to be for convex functions only. But they have countable. There's, for example, there's only exactly one point where it was not differentiable, right? So countable number of points of non-differentiability. So that's what subgradients give you. Okay, I'll just yeah. So we'll deal with more with subgradient calculus. This is actually the notion of subgradient calculus. You can also have sine and cos, etc. And mostly derivatives can be obtained with the basic derivative rules that we have already listed above, with the right choices of product, division, addition, chain rules, etc. It's also basic principle of autograd. Now you can also have partial derivatives when you're stacking up derivatives of a function with respect to individual components of a large random vector, right? So, for example, if you are dealing with gradient of a function, you need partial derivatives. So if you have gradient of f with respect to a bunch of variables x bar, the way you would handle it is gradient of f at x with respect to x1 and again stack them up to xn. This is a gradient. And you can now do the same thing for all the rules that we talked about. You could apply here to each partial derivative. So if, for example, if f itself is say f1 of f2 of x, right? I'll put a bar here. Then you could have a similar invocation of chain rule, but for every component. So then you'll have the partial derivative of f with respect to x1 is a partial derivative is the basically now the derivative of f1 with respect to f2, and then the partial derivative of f2 with respect to x2. So we have done this here. For example, if you have 3x1 square x2, then it's a combination composition. So I've applied the partial derivative for each component by using the basic rules of derivative. Okay. So this takes us to the next topic of gradient. So you have a vector w equals w1 to wm. So the loss gradient at w is defined as the partial derivative with respect to the first component of the weight and so on, stacked up to the last partial derivative with respect to the last component of the weight. So we can write this ideally we write all of this as column vectors. These are all actually column vectors if you put a transpose, but sometimes for simplicity of notation we drop the transpose, right? Okay, so by default all vectors are column vectors, but sometimes we drop the transpose on the row vector even while denoting the default column vector. Okay, so this is just a convenience for sometimes for simplicity of notation. So especially when it comes to chain rule on vectors, chain rules on composition, you can remember that column vectors are what we use by default. So for example, if you have L w1 comma w2 is w1 square divided by w2, then you can compute the gradient as follows: 2 w1 divided by w2, that's the gradient with respect to partial derivative with respect to w1, and the second component is the partial derivative with respect to w2 minus w1 square by w2 square. Okay, so likewise you can also compute the Hessian. Again, I request you to ask me questions if you have at any point of time. I'll assume we are doing well otherwise. You can also compute the Hessian of a function. Now Hessian is basically set of all these double derivatives and mixed partial derivatives. So here you see an example. Sorry. Yeah, this is say a mixed partial derivative of the partial derivative of f with respect to w2 with respect to wn. We refer to these as mixed partial derivatives. And there are some other the diagonal entries are all about double derivatives. Okay, if there are questions, please ask. Now, when do you think is this Hessian matrix symmetric? Anyone? Let me ask this question. When is this matrix symmetric? Anyone?
So when the order of the differentiation doesn't matter?
Yeah, but when does it matter?
In convex functions?
Not necessarily.
Okay.
The answer is when, yeah, when the order of derivatives, differentiation rather, don't matter. And when it doesn't matter is basically when these mixed partial derivatives are continuous. Okay, so continuity is good enough a condition. Is that clear? If they are continuous, then you're done basically. Fine. Any questions? Please let me know. For example, if you wanted to compute the Hessian of the function W1 square by W2, right? So it's simple. I mean, mixed partial derivatives come here. So derivative with respect to W1 gives you 2W1 divided by W2, and then you take a derivative of that with respect to W2. Okay. I hope this is clear to everyone. And you can see that this is actually symmetric, right? These two entries are exactly the same, and that's because they happen to be continuous. The order of W1 and W2 is not mattering. Sorry, I didn't write it very clearly.
Sir, that function, so if the value of W2 equal to 0, then it will not be continuous, right? So it should be in range.
Right. So this is exactly, this is not even defined. If W2 is 0, it's not even defined. You're right. But all the places the function is continuous, right? And therefore the Hessian matrix is symmetric. Okay. Let's now look at regularized logistic laws. So the labels are just say +1 and -1. The objective function is this lambda by 2 norm W square plus summation over all the data points of the log of 1 plus exp minus the yi w transpose xi. So yeah, I would like you to verify that this is indeed the gradient of the loss. Okay. So the gradient will basically consist of vector. So there's a w is a vector here. Xi is a vector here. So keep all that in mind. Make sure the dimensionalities match. That's indeed the case. So if the dimensionalities don't match, then there's something fundamentally wrong with the expression itself. Okay, so how exactly would you compute this? So the expression is given here. How would you arrive at this? You have a log of a 1 plus exp, right? Summation is outside. So what would you apply?
So there'd be a chain rule, I guess.
Exactly, chain rule, right? That's as simple as that. From log to dxp, right? So now exp itself is exp of minus yi w transpose xi is basically a summation. This is itself a summation. Okay, so we may want to note that down. Think of this as wj xij, summation over all the j's. And when we're talking about gradient, we're really talking about the partial derivative of L with respect to wj. Okay. So compact notation helps, but can also be deceptive. So when now you want to find the derivative of this summation with respect to the jth component, all others will disappear. The summation, however, will persist when you now look at the derivative of the exp. So you'll have derivative of exp coming out, but this x, you see why this xi comes out. Okay, the xi come out for two reasons. Sorry, one is xi is because of the summation over I, and then only the jth component of x is going to matter here, or the jth vector. So that's how the xi has come out. Okay. So please let me know if you need help in this kind of derivation. Otherwise, I'm going to progress. Anyone?
Sir, just for the sake of understanding, could you show the steps that you are talking about? For example, the compact representation to the summation and all.
Okay. So good point. What we will do is maybe this part is clear, right? So this W transpose xi is summation over j wj xi.
Yes,
Now
sir, this part is clear.
let's go chain, just apply the chain rule one by one. When you have exp of minus of this entire factor, the derivative of that, partial derivative of that with respect to wj will just remain the negative of the exp, right? So I'm going to use the fact that I have an xij component from here. So let me write this down here. But let me write it here itself. Okay, so here you have jth component. So the log of 1 plus exp, that's another composition, and that will be basically 1 upon 1 plus exp. Let me erase this part. It will be a little challenging doing it on this small space, but I'm going to give you the spirit of the derivation. Okay, so log of 1 plus exp. Oh, sorry, there's a summation as well. There's a summation over all I. The summation over I, 1 of log of exp, and I'm not going to expand this. And then the exp, 1 plus exp, right? The chain rule. I'm just applying chain rule. That'll only have the exp part. The derivative of this 1 will basically disappear, right? And there'll be a negative sitting out here because of I have a minus of yi. So I'm going to write this down. I'll have this minus yi coming out here. And the exp of w transpose xi. Okay. So why is yi coming out? Yi is coming out because of so actually I should write it here. This is not just wj yj, wj xij. This is wj xij yi. Okay, so that yi has come out here because of that. I'll put the negative as well, and you will have only the xijth component coming out here because the wj would have disappeared by virtue of the partial derivative into the exp term as usual. So let me just highlight this green part is as it is. There's nothing going on here. The log that has led to the division, right? The log has led to this division by 1 plus exp. The fact that I was trying to find a derivative with respect to exp of minus, as that has led to this exp of this term has come out as it is. Again, it's come out. It's just a copy. This exp term has come out as it is. So the only term that has come out here sitting out in pink is because the derivative of this summation. So let me write down this the partial derivative. I need to string this. Okay, so the partial derivative of this entire summation with respect to wj is exactly this minus yi xij. Okay, the part here inside in pink. Okay, and that exactly, so that is the part we have written out here. Okay, this partial derivative. Sorry, I'll need a different color. This part has what has led to what remains here. Is this clear now? And when I just unroll this vector, this is a vector, right? If I take the, I can take the jth component on the jth row of this column vector. So when I stack them up, all these xj's, everything else will actually come out. Okay. So you were saying something?
No, sir. I understood the last part that you were trying to explain. I got it. Thank you,
right.
sir.
Right. So everything else comes out except for this xij. Xij stays back, and that's where you get a stack of xij's in the form of this xi vector. So everything boils down to this xi vector. Okay. Yeah, but unless you use pen and paper, there's only so much you can get, right? So like we did the gradient, you can also derive the Hessian of mixed partial derivatives. Okay, so I'm going to leave this really as homework. Make sure each and every one of you gets this form. Yeah. Okay, and then thereafter, I'm going to leave you with this homework as well. You please try and now not only derive for the logistic loss, but I've given a combination here, a bunch of combinations here. For example, we looked at hinge loss SVMs. Here is a least squares loss. Two layer functions, right? You have a hinge loss followed by this difference from yi squares, and finally the softmax function. So try and derive the gradient and Hessian for these loss functions as well. Okay, thanks. We have reached the time limit. We can have more questions in the next class. Please brush up this part. Thank you.
Thank you, sir.